We're going to start talking about shellcode, and I think we'll do lunch like at 12, like 12 to 1. How's this sound, everyone? And I want to get through a basic example of shellcode environment, and then you guys are going to have a lab where you actually develop your own shellcode. And then I want to get up to that point, introduce the lab to you by the time we leave for lunch. That way, if any of you feel especially motivated, you can have a shorter lunch and work on that over your lunch break. Because that'll be one of the trickier labs, I think. So, it was cool that we exploited this full login program. We got it to run the Go shell function even though we gave it a bogus password. However, it was kind of lame in that we were relying on this pre-existing Go shell function to do our bidding. And that's not exactly arbitrary code execution. Remember I said at the beginning of the class our goals are always arbitrary code execution. That isn't exactly arbitrary because we're relying on this pre-existing code that we didn't design ourselves. We want to be able to cause the program to do anything, to open up calc.exe or bind a shell to a port or something like that. And the process of doing that is shellcode. Essentially what shellcode is a small mini program that you inject into the input of another program, and you redirect EIP once you gain control to that mini program with the shellcode that you've developed, and that mini program will do whatever you want. So examples of real shellcode is something that does like spawning a shell. That's real shellcode. If you're looking at a local Linux exploit, it'll spawn a shell in a root process and it'll have root on the box. Or in the Windows world, it might go to a prefixed web address and download and execute a file there. Most commonly, it's a rootkit or something like that. Or it'll bind a shell to a port, and then the attacker can then connect to that port and then issue commands if that's like a remote exploit. What you usually see in like an enterprise scenario when you have firewall set up, you can't, just spawning a shell doesn't do anything because the attacker has no interface to that shell, and just binding a shell doesn't do anything because normally the enterprise is behind a firewall. So common like enterprise attack shell code is something that will go out and go to a fixed web address and download and execute an executable, and the attacker will store some rootkit on some hijacked website, and then the shellcode will go and download and execute that shellcode. Or you also see something like connect back shellcode, which is the mini program, the shellcode will connect to a prefixed address, some compromised server, and listen to whatever that server tells it to do, and it'll start reading in commands and executing those commands. And that will sort of bypass the firewall because you're going out, someone isn't coming in. So that's just a couple examples of real-world shellcode. Our first example is going to be Hello World shellcode, because that's the first example for all kinds of programming. But of course, there'll be a different spin on Hello World because it will have to be one of these mini programs, these shellcodes, and that makes it a little bit more challenging than your normal Hello World style program. Okay, so let's talk about some properties of shellcode before we even try to develop some of our own. First of all, it usually has to be pretty small. For instance, programs, even ones to print Hello World, are usually pretty big. If you were to look at the size of a Hello World executable in Windows or something really simple, that's another trivial program, it would be huge. It'd be like 4 kilobytes, right? And that is that is bad as a disadvantage for the shellcode because let's assume we're overflowing something like the password buffer. This was only 64 bytes long. So essentially what that means is that our shellcode would have to be less than 64 bytes, okay? And so 64 bytes is pretty small when we're talking about code as you develop. So you always want to make your shellcode as small as possible. Position independent. Usually, when you have a program like Hello World, you'll be passing an address to a function like printf. And so like printf address, and that address will be the address of the Hello Yeah, pushing the address in the string to printf. And this program would not work as shellcode because in this case, they're assuming the hello string is located at this address. It's like a fixed address, you know? And so if this was a mini program, a shellcode that we injected into another process, this address would basically be bogus in the victim process address space. So it would try to print this address, and in the victim process, the process that we're hacking, this address would point to something with Linux assembly is actually pretty easy, which is what we're going to do. For our hello world example, we're essentially going to program assembly to call the write function and then write the hello world message. So write some buffer containing hello world to standard output, which is just 1, and the size of the message. So we basically just have to call that function from assembly, and that's not too bad, because Linux has this handy-dandy convention where each system function, each system call is assigned a number. So write is assigned like the 1, and create files like 2, and delete files like 3, and read is like 4. Those are wrong, but each one is assigned a unique number basically. And then to call a system call, you basically set up the register so that EAX, first register, contains the number associated with the system call. EBX contains the first argument, ECX contains the third argument, EDX contains the third argument, and so on. And then once you have all the registers set up with the correct values, if you interrupt OX80, the operating system will intercept that and say, okay, I detected that this program wants to execute a system call. I assume the registers are set up correctly, and I'm going to use those registers, EAX through whatever, to perform the system call. So it's really pretty simple. Okay, so yeah, I should point that out. So these numbers I was mentioning, I said that each system call has a unique number associated with it, and you can actually find out where these are by looking at this file, /user/include ASM x86 blah 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 .h. I'll bring that up right now. I mean, I've got to tell you what all the system call numbers are in this class, but in case you want to see the other ones.
Is that a standard convention in all Linux system calls that arguments are in the order of are placed in the order of the registers? EAX, ECX?
That is for system calls only, not for functions. Yeah. Standard libc functions pass their arguments on the stack, like I was showing you before. They're pushed, but as system calls, you pass the arguments by register. So it's just different because you're calling different things. You're not just calling a general libc function. You're actually telling the operating system to perform some all-powerful function, and the operating system has to handle that. So it just has to be done a little bit different. If you want to learn more about why that is, you probably take, I think Vito talks about that in his intermediate class. Oh, no. I already forgot to do that talk. Someone tell me what that path was again? It was like ASM. I386, is that right?
Yeah.
And then, yeah, so all the unique numbers are there. So you can see that the read is, 3. So if I wanted to call the read system call, I need to set EAX to 3. If I wanted to call write, which is what we want to call to write our message to standard output, EAX has to be 4, open, close, create, unlink, which is like delete file, blah, 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 blah. You can see all the awesome functions that Linux lets us call. And you can call any of these from assembly that you want. Let's say I want to call the fork system call. I can see EAX needs to be 2 because that's the number. Then I would do man fork for the manual page for fork. And this one's pretty simple because it doesn't have any arguments at all. So I would just have to set EAX equal to 2 or whatever it was, and then do interrupt OX80. Yeah, question?
Some of those are privileged though, right?
Yes. Yeah. Obviously, you're not going to be able to do anything you want based on what your user privileges are in the system. But it would be up to the operating system to make that determination. You could try. You could set up the system call and do it, and the operating system would basically just say no. And set EAX equal to -1 to let your program know that you did not execute the system call successfully. So that was actually kind of a bad example since there were no arguments. Let me choose another one. So exit, that one's easy. So exit is system call number 1. And it just has one argument, which is the status. So exit 0 means like there was the program executed successfully, or exit -1 meant it terminated the problem. So if I wanted to call this as a system call, I would say EAX equal to 1 and EBX equal to whatever status bit I wanted to exit with. And then I into our string. And then edx equals 8, which is just the length of this string. And then once I do interrupt OX80, the operating system intercepts that interrupt and says, okay, the program wants to execute a system call, but I assume the registers are set up. I see he wants to do a write system call, those are the things, so I perform it. And there it is, you get hello on the screen. So just to make sure we can all compile and link this stuff correctly, let's all compile and link the basic Hello World shellcode, or the basic Hello World program. This isn't shellcode yet. So these are more commands that you're going to want to write down, by the way. So first off, all of these files for the Hello shellcode can be found in the student home directory. So, and then the Hello shellcode directory, so if you do hello cd hello underscore shellcode, you'll see all the files are in there. The one we're dealing with right now is hello1.asm, which just contains what I showed you on the slide. And then to compile and link this thing, write these commands down just so you guys know. NASM, which is the net wide assembler, -F for format, L, which is the Linux executable format. Hello1.asm. And then you also have to link the program. So yeah, I would just add that to your list of helpful commands. NASM, LD, yeah, there you go. So there you go. You know, Linux assembly isn't all that bad. It's actually pretty nice. Once you get into the Windows world, things get pretty hairy. And if you take exploits 2, you'll see why, basically. So I'll just give you guys all a minute to make sure you can compile and run that. So, you know, no surprise there, simple program, easy to compile and run. And the Hello World program at this point is not suitable as shellcode, even though we've handcrafted it in assembly, because there are some issues that I'll point out. So first off, let's start looking at this as shellcode and trying to convert it into something we can inject into another process and then point the return address at. Okay, here's another command for you guys to know. And it's objdump-d hello1, which basically means object dump does all kinds of fun stuff on Linux executables, and D is just disassembled. Hello1 is what I named our Hello World, our compiled Hello World executable. And this just will show me the program bytes for our Hello World program and what they actually correspond to in x86 assembly. So we can see that move 4 into EAX, by the way, this is in AT&T syntax, not Intel syntax, just be aware of that. But basically, you know, move 4 into EAX, this corresponds to these opcodes, you know, processor opcodes. Move 1 is this. Interrupt OX80 is these. So here you go. We want to convert this into shellcode, something we can inject into the password buffer and then return into that. So we haven't really tried to make this shellcode yet, but you can go ahead and tell me one thing you may see wrong with this that disqualifies it from being used as shellcode.
The address that's where it's set.
So eventually we will inject our shellcode into like the simple login program or something like that. And this address, the simple login program, is not the same as what it is in the Hello World program, right? This address will probably be meaningless in the Hello World program. And that's because, of course, in x86 protected mode, each process gets its own unique 32-bit address space. Okay, so remote users, remote guys, can one of you point out another issue with using this as shellcode? The string, it would only copy 2 bytes. And obviously, we need it to copy like 72 bytes for our exploit to be successful. So those are really the main issues. The exit thing isn't a problem because the exit one is actually a system call as well. And in this case, we're just going to get it to print a message and then exit, and that's just what we wanted to do. So it's no big deal. The main issues here are the absolute address. This address is bogus in any victim process address space, and all these null characters that we got to get rid of. So the easiest thing to do is to get rid of the null characters, actually. So I think that's what I do next. Okay. Oops. Yes. Sorry. So for the next phase of the shellcode, we're just going to try to get rid of the null bytes that appear in the shellcode. Okay. Because that's kind of easier than dealing with the absolute address at this point. So the reason we got all those null bytes is because we tried to move a value into a 32-bit register. So if you'll recall, in the last phase, this was something like move EAX 4. And EAX is a 32-bit register. So when we try to move a value to it, the assembly automatically wants to basically consume the whole 32-byte register, so it's going to pad out the rest with zeros. Now, there's this cool thing you can do in x86 to address subsets of the EAX register, only other parts of it. So when I say move AL4, I mean don't set EAX to 4, just set the lowest byte of EAX to 4. Let me draw that on the board. This is a little bit crazy. Okay, so in x86, registers are 32 bits, right? Everyone's with me there. So we have something like EAX. And we'll say these are EAX's 32 bits here in Ireland. And let's break it up into it's 4 bytes, okay? Because 32 bits is 4 bytes. Everyone's in there too, right? So x86 actually has a cool way where you can address individual parts of the register. So if you tell the assembler to use EAX, it's going to automatically assume the whole 32-bit register. If you tell the assembler AX, instead of EAX, it's just going to address the bottom 2 bytes, the lowest 16 bits. And if you were to say AL or AH, you'd be talking about this byte or that byte. Notice that you can't address these individually. That's just kind of a limitation. You would have to use like a bitwise arithmetic if you wanted to mess with these individually. So if I just wanted to set this to 1, I could just do move AH1. And let's assume that this is like, you know, F, 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 F. The time that I execute this, the end result would be EAX equals F, 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 0, 1, F, F. And then if you were just, look at AH individually, it would still just come out as 1. You guys follow that? Remote users, you okay with that?
Sure.
Okay, yeah, then not too bad. I don't know if there's anything like that in ARM, but that's just kind of a weird thing that x86 does. So, like I was saying, whenever you want to set EAX to a value, like with our Hello World shellcode, we want to do something like move EAX 4, because 4 is the number for the write system function. It's going to automatically, since we're messing with a 32-bit register, it's going to pad this out to be like 00, 00, 00, 04. That way it can come.
Value of 4, you need to ensure that they're all 0 in the other.
Excellent question. Anyone have the answer to that? So what you should do first is zero out the entire register before you change AL to 4. So you want to make sure that EAX is equal to 0 before you set AL equal to 4. That way the whole value of EAX is 4.
Is there
But the problem with that is you put in 0, so you have to set FF for FF.
Yeah, so, there's a question. How do we set EAX to 0 down in null bytes? Yeah.
He sets all less and then do an add 1.
You can do that, yeah. There's an easier way.
XOR with itself.
Yeah, XOR with itself. And the advantage there is that the XOR with itself only takes up two x86 bytes to represent the XOR anyone tell me why this still isn't good? What's the issue? There's a bad byte in there somewhere. I'll give you a hint. Can anyone recognize what the bad byte is? It's actually the 0A character. It's the new line character. So what happens is when I had that in my message string, that 0A new line character, which basically is just the new line in my own message, the GETS call that reads in our password attempt sees the new line character and assumes that that means you press enter and are done entering in your string. So that's another byte you have to avoid. So what I did was I just changed the 0A character to another exclamation point. Yeah, kind of cheating. And another sort of nasty thing or sort of tricky thing that I did here was that I made the message exactly divisible by 4 bytes. Okay, so it's 8 bytes in total is the length of the string, divisible by 4. And the reason I did that is because you can only push 4 byte values onto the stack. So it would have been a huge pain trying to write a message that wasn't divisible by 4. Or it would have been more. Wouldn't be. So I think what we can do actually, well, I just want to make sure this actually works. I put the final version of the shell code in hello4.asm. So you can kind of see what's going on there. And like Pete pointed out earlier, I went ahead and just exported those registers out to be safe, zeroed out all those registers before I just started changing individual bytes of them. And so this is really nasty looking assembly compared to our original Hello World program, but it should be good as shellcode. And so we can just verify that it still works, which is something you should generally do. Notice we don't get the new line in the message, right? This time is because I just changed it to that exclamation mark. So it still works, and when we look at it with that objdump command, objdump-d for disassemble, you can see no null bytes, no absolute addresses, should be all good. So if we were to put this in the password buffer, then overwrite the return address and point it back at the password buffer where this is located, we would actually end up executing this mini program that we just injected into the vulnerable victim process. Which is kind of cool. We've taken one program and basically turned it into another program by exploiting this vulnerability. Okay, so actually, do I have you guys actually? Yes, I do. So that's I'm actually going to have you guys use that shellcode just so you can get a feel for using a shellcode that we know works and exploiting a program before I have you guys develop your own shellcode and use it to exploit another program. So we're going to use that Hello World shellcode that I just showed you to exploit the simple login program. So, to really use this shellcode though, we can see this is the objdump output. We have to sort of recreate these, these binary bytes in the password buffer. So remember how we create those addresses like the Perl print \x. We have to do that for these. That way we can just get Perl to generate this mini program for us on command. So I've actually provided you a nice little Perl script to do that. So you can see basically I just took the output of that objdump command. You can see the opcode bytes here in the string as well. So B001 is down here, and then 31db, 31db, 880, because these are just x86 opcode bytes. So if the instruction pointer is pointing at these, it's going to know what to do with them, because And what we're going to do is have the simple login program, instead of executing Go shell, execute our hello world shell code. So instead of spawning a shell or printing the wrong password, it's actually going to print our message. And that's significant because we're causing it to execute our own mini program that we custom developed, which means we could, we have arbitrary code execution because of this vulnerability in simple login program. Does everyone understand what we're going to do, the strategy here? So I'm going to walk you through this process so you guys can do it on your own a little bit later. Does everyone understand where this Perl script came from? How it represents the opcodes of the shell code? Remote users, do you follow that as well? Just want to make sure, because I know that that part can be a little bit weird.
Would it be useful to have like a Perl script that
I know,
punches that object?
someone asks about that like all the time. And yes, it would be. However, at this stage in your exploit development career, the more suffering, the better. All right?
Okay.
The more stuff you have to, I don't know how to say this to be mean, the more stuff you have to do by hand, instead of going to Metasploit to generate shellcode, doing shellcode yourself, the more you have to do by hand, the more you're going to learn. This is a guided learning experience. It's all about learning. So, yes, in reality, when I'm developing an exploit, I have some magic script where I use Metasploit to automatically generate my shellcode on the fly. But if you really want to be good at this stuff, you have to know how to do all of it manually. Period. So, all right, so it looks like the remote users are still on board. So let's just talk about sort of draw on the board how we're going to generate our payload file, what the stack's going to look like, and then we're going to actually develop the exploit and simple login program. So let's come back to the board over here. Back into stack land. So this is going to be the stack right after the Gibbs call, right after our password attempt has been inputted in again. I'm just going to show you what would the stack look like eventually. So essentially, we're going to have our shell code. So say like x31, x c0, x31. These are just the bytes, and I'm just copying down off the shell code we got here. Blah, 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 blah. The hello shellcode is not 64 bytes total, okay? That's only like 30-something bytes. We're going to need to completely consume the password buffer, though. So we're going to have some some padding value in here. So, this is all the shellcode. We'll say this is 30 bytes. I'm guessing. I think it's actually something else, but it doesn't matter for now. 30 bytes, which means we would need like 34 more bytes of padding to completely consume that password buffer so we can get you the important process metadata like the return address and the safe frame pointer. So 30 bytes of this, so we'll say like A. And then, so after that, we will completely consume the password buffer. We can just put B's again for the saved frame pointer. We don't care about it. And then what will we put for the return address? Can anyone tell me what the return address will be? Approximately? We have shellcode, padding, B's for safe frame pointer, and we need to override the return address. Previously, it was like 0804 blah blah AA, which was the address of Ghost Shell. This time, we want the return address to point back into the stack to where our password buffer is, because that's where our main program is. Okay. So this is going to look, the stack addresses are like BF, so equals F, question mark. We'll discover that later. Now, the payload I've described up there actually isn't optimal, and that's because in order for our execution to work, our return address would have to hit the first byte of that shellcode exactly. If it hit anywhere else, like halfway in the shellcode, it would probably crash because it has to execute everything precisely for that shellcode to work. For instance, if we pointed the EIP, return address has to point right here exactly, okay? If it ends up pointing right here, all of a sudden, well, this would probably crash because it's inside the middle of an x86 instruction. Right? And this would not be a valid x86 instruction because this instruction is technically supposed to start here. Or let's say it started right here, which is valid, but we've only executed half our shellcode, so we didn't initially zero out the registers and we get a crash. So the whole shellcode has to be executed starting at the first byte. So one thing we can do to help ourselves out is using no-ops. So a no-op instruction is a 1-byte instruction that basically does nothing. And what this means is that if we were to make our payload something like so no-op equals OX90 means do nothing. 90, so now, and then put our shellcode here. So let's say our shellcode is 30 bytes. That means we need 34 bytes of no-ops. And then let's put S for shellcode, because I keep forgetting what the opcodes are. This is 30 bytes. Which means these two together are 64 bytes. Which means we'll have no ops and then our shellcode completely assuming the password buffer. And we're going to write 4 B's to overwrite the frame pointer. And what this does for us is the return address can then point at this, or this, or this, or any one of these 34 no-ops, and we'd be okay, because we'd execute one, then the next, and the next, blah, 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 and then start executing our shellcode. Doesn't matter which no-op we start on, because eventually we'll slide down the no-op slide is what they call it, until eventually we get to our shellcode, and we'll start executing our shellcode from the first byte. So what this allows us to do is to have multiple valid return addresses that will cause our mini program, our shellcode, to be executed. And this is critical in exploit development because you want to have a little wiggle room, because often you'll develop, for instance, an exploit for your system, and you want it to work on someone else's system, and their stack addresses will actually be a little bit different. So you want to have sort of like a lot of padding of valid addresses so that there's greater reliability that your exploit will work, because their system is a little bit different than yours. Say they're running source stack 2 instead of source stack 3 or something like that. So having those extra no-ops in there just gives us more valid addresses we can return to and increases our odds of success. Everyone follow that? Remote users, network guys, you okay? There are some in the exploit community that would actually frown upon using no-ops and stuff because they want everything to have surgical precision because it's very skilled. And yeah, there's some argument to that, but when you're trying to develop an exploit that works, you do what you got to do. Okay. So some important points here from this slide, just to reiterate on, is that the no-ops plus the shell code needs to be 64 bytes. Everyone understands why that is, right? Yep. To completely consume that buffer that we're overflowing, the password buffer. 4 bytes of junk don't matter because we do not care about the state frame pointer at this point in the class. And then the address of the password buffer or the address of one of our no-ops in particular. Because if we can execute one of our no-ops, we'll eventually slide down to our shell code and be okay. So this is what our payload file is going to look like. It's going to cause a stack to look like what I drew on the board, and then hopefully our shell code will be executed. So let's go through the process of developing our shell code. Okay. So first I wanted to see my shell code in a file. I'll leave those commands up for a second, but you can see that, you know, just put these hexadecimal bytes into this file for us. And this file represents the shell code. The next thing that we're going to want to do is figure out what the actual size of our shellcode is. I guessed that it was 30 on this, but I think it's something else actually. So you just do, oops, that's not right, sorry. WC shellcode, like word count shellcode, would just tell us the number of bytes in the shellcode. So in this case, yeah, I actually got it backwards. The shellcode is 34 bytes, not 30. So that means we need to have how many bytes of no-ops in our payload? 30. And which should come first, the no-ops or the shellcode in our payload file?
Shellcode.
The no-ops. So we need, let's go ahead and start constructing our payload file. The no-ops come first. is there going to be, if you remember when I drew on the board what the password buffer looked like, the P in password was at the very bottom of the stack. And we want those no-ops to be at the bottom of the stack. That way they get executed, the EIP keeps getting incremented and going up towards our actual shell code.
The no-op is hexadecimal 90.
90. Did anyone know what no-op actually does?
Yes. It does an exchange.
What register? They exchange what? With what?
With EAX, I think.
Yeah, who was it that said that? Because I know you've taken Zeno's class if you know that.
Yeah.
So yeah, we were at super nerd trivia trying to impress girls one night. Remember that? You know, we'll have wild success. So yeah, no-op doesn't change EAX, which is basically nothing. So let's start constructing our payload file. First thing we want to do is print those no-ops out first. And we want to print 64 is the size of the password buffer, 34 is the size of the shell code, so 35 is in total. Just make it explicit up that the arithmetic in there. Then I use the cat command just to put the contents of this file and append it to this one. For those of you not familiar with Linux, you might want to write that one down too. So at that point, that's what our payload file looks like, and at this point, it should be 64 bytes. Okay. So at this point in our payload development, we're at the point where we will be overriding the save frame pointer. Okay. We don't care about that, so we're just going to tack on 4 bytes of junk. Now, what should the next value be in the payload?
Address is, no, so no op there.
Yeah, return address into the no-ops, or if you wanted to be fancy, you could try to hit the first byte of the shell code too. But what is that address? Everybody knows, right? So
Whatever ESP is.
yeah, but where is ESP? So what I want you guys to do is, I'm not going to tell you how, I'm going to see what solutions you can come up here with for a minute. And I use the debugger to try to find out what we should use as the return address for our payload.